So picture this. This morning, I was pouring myself a cup of coffee, and I was, really trying to hit that little fill to here line on the inside of the mug.
Oh, yeah. Like trying to get it exactly on the line.
Exactly. I was being incredibly careful. But, I mean, no matter how steady my hand is, I never land exactly on it. It is literally always a microscopic hair under, or like a tiny fraction of a drop over.
Right, because realistically, you couldn't land perfectly on it if you tried a million times. There is simply no physical way for you to pour liquid to precisely that line right down to the last invisible sliver, atomic layer by atomic layer.
Yeah, that is exactly what I was thinking while I was just staring at my mug.
Yeah.
I started wondering, what actually is the chance that I pour to that one mathematically exact line?
Yeah.
And intuitively, it just felt like the answer had to be 0.
Yeah.
Hitting one single infinitely precise spot in the physical world just seems impossible.
Well, that mundane observation over your morning coffee is the exact puzzle driving our sources today. We are looking at situations where a value can land absolutely anywhere within a continuous range.
Okay, so like the coffee level.
Right. Think about the level of coffee in your mug, or the fluid sweep of a clock second hand, or the exact moment your bus shows up at the stop. When you are dealing with a continuum like that, asking about one exact isolated value completely stops making sense.
So if I'm tracking when the bus arrives and it can show up at literally any fraction of a second, I just can't ask about the chance of it arriving at exactly 8.14 and 000 seconds anymore.
Right. You have to abandon the exact value entirely. Instead, you have to ask about a range.
Oh, okay.
You ask about the chance that your coffee landed somewhere between two specific millimeter marks, or, the chance the bus arrives between 8.10 and 8.15. That conceptual shift, moving away from exact points and focusing strictly on intervals, is the fundamental premise of continuous random variables.
Okay, so if we look back at the discrete math you might be used to, the variables were always these tidy, finite lists, right?
Yeah, exactly.
You flip a coin, you count 0, 1, 2, or 3 heads, or you roll a die and get a whole number. What fundamentally breaks that old system here?
Well, the nature of the variable itself has changed. The values you're looking at now are measurements, not counts.
Right. Measurement.
Take the waiting time for your bus. That can be any positive number from 0 upwards. Or check the temperature outside this afternoon. That can be any reading on the thermometer. Or spin a dial on a board game. It can stop at literally any angle.
Yeah, and I guess the defining feature of all those measurements is that between any two values you pick, there is always another one hiding in there.
Exactly.
If I measure 70 degrees and 71 degrees, there is 70.5. And between 70.5 and 70.6, there is 70.55.
There are infinitely many more values crammed between any 2 points. And that infinite density is what breaks the old discrete approach.
Because there's just too many of them.
Right. Because you have an endless number of possible outcomes packed into a space, the slice of probability assigned to any one specific exact value is infinitely thin. So the probability of any single exact value is 0.
Wait, really? Meaning, if I try to use my old probability rules and I ask, what is the chance the bus wait is exactly 4.000 minutes,
Yeah.
I am asking a fundamentally broken question.
Yeah, totally broken. The math will just hand you a 0 and refuse to cooperate.
Wow.
We need a completely different mathematical tool, one built specifically to track ranges and accumulating totals instead of isolated individual points.
But if individual points give us 0, how do we even begin to define a continuous variable mathematically? We need something that tracks a running total, right?
Yeah, so we use the continuous cumulative distribution function. The underlying logic is the same as the discrete version, basically. The CDF, f of z, represents the probability that your variable z is at most z. It acts as a running total, sweeping up all the probability from left to right. But a variable is only considered continuous when that CDF, f of z, is a genuinely continuous function.
And when you say continuous function, you mean there are absolutely no jumps or gaps in the graph?
Right. You could take a pencil and draw the entire curve from left to right without ever lifting the graphite off the paper.
Oh, that makes sense.
Contrast that with a discrete CDF. A discrete running total looks exactly like a staircase. The graph runs flat, then it suddenly jumps straight up at a specific counted value like rolling a 3, then runs flat again, then jumps again.
Right. Those vertical jumps happen because all the probability is piled up on those exact counted values. 1 head, 2 heads. But with measurements, there are no steps.
The staircase smooths out entirely. It transforms into one continuous flowing S-curve. It starts at 0 on the left, sweeps smoothly upward as it accumulates probability across the range, and levels off at 1 on the right. That unbroken smoothness is the visual signature of a continuous variable.
Okay, so if we are operating in this new mathematical reality governed by a smooth S-curve, what are the practical consequences for you, the person trying to actually calculate something?
Well, two very strange but convenient things fall out of this. First, it mathematically confirms your coffee mug dilemma. Because the curve has no vertical jumps, no single point adds any sudden probability. Every single point really does carry zero probability.
Which raises a really practical question for anyone trying to set up an equation.
Mm,
Does the difference between the phrases less than and at most even matter anymore?
not at all. That is the second consequence. The probability that your variable z is between a and b is the exact same whether you include those boundary endpoints or ignore them.
Oh, wow.
Yeah, the endpoints themselves carry absolutely zero mathematical weight.
I have to say, that is a massive relief.
Mm-hmm.
I mean, in discrete probability, you have to obsess over every single endpoint. If a problem says less than 3 versus 3 or less, you get completely different numbers.
Oh, for sure. You can entirely stop fussing over endpoints now. But this convenience comes with a major catch.
Uh-oh. What is it?
The foundational rule you used for discrete variables, where f of z is the probability that z equals z, is now completely useless.
Wait, completely useless.
If you try to use it, it just gives you zero everywhere. It tells you nothing about how the probability is actually behaving.
So our primary tool is just dead. What do we replace it with? I mean, how do we measure anything if the points themselves are zeros?
We look at how steep the curve is. We introduce the probability density function, or the PDF.
The density.
Right. Instead of trying to measure probability exactly at a point, this density measures how probability is packed near a point. Mathematically, the density is simply the slope of our S-curve. So f of z equals f prime of z.
Okay, so we're measuring the slope. Where the S-curve climbs steeply, the probability is dense, and where it flattens out, the probability is thin.
Yes, exactly. And this creates a profound shift in how you solve these problems thanks to the fundamental theorem of calculus.
Okay, bringing in the calculus.
That theorem tells us that the probability z lands between A and B is the area under F from A to B.
Let me just make sure I'm visualizing this clearly. The conceptual leap here is that probability has physically transformed into geometric area.
That is exactly the visual you should have. If you want to know a probability, you define your interval, you shade the region under the density curve between those two marks, and whatever that shaded area is, that is your probability.
Okay, got it. So for a function to act as one of these density shapes, what are the ground rules?
The rules perfectly mirror the old discrete rules, just adapted for a continuous shaded area instead of isolated points. Rule 1. The curve can never dip below the axis. The density, f of z, is at least zero everywhere.
Because, yeah, negative probability doesn't exist. You can't have a negative area representing negative odds.
Right.
What is rule 2?
The total area under f is 1. Your variable has to land somewhere in the universe, right? So if you look at the entire curve across all possible values, that shaded area has to add up to exactly 100%.
And the smooth S-curve we talked about, the CDF, it just accumulates that area from left to right.
Exactly. It just sweeps across, adding up the area as it goes. Any mathematical function you can dream up that is non-negative and where the total area under f is 1 is automatically a valid density.
Now, if your calculus is a little rusty, hearing phrases like fundamental-theorem and accumulating area might sound pretty intimidating. Do we need a massive textbook of calculus rules to survive these deep dives into continuous math?
You really don't. You only need a surprisingly small practical toolkit.
Phew.
Yeah, you need to know how to take a derivative to find the slope of the CDF, and you need to know how to take an integral to find the area under the density.
So what are the bare minimum rules we actually need to use?
Well, the power rule covers most of it. You bring the exponent down and subtract 1 for derivatives and do the reverse for integrals. The derivative of e to the x is just e to the x. And going the other way, you just need the integral of x to the n.
Okay, that's not too bad. And when we actually calculate the physical area for an interval?
You lean on the fundamental theorem. You find the antiderivative, which is your f, and then you just evaluate it. You plug in the top boundary, plug in the bottom boundary, and subtract the bottom from the top.
Simple enough.
And honestly, for anything weird or complicated, you don't even need to do it by hand. Just use a standard integral table. The actual skill is setting up the correct boundaries. Let the table do the heavy lifting of finding the formula.
I wanted to test that idea immediately. Let's look at something from our sources that isn't just a basic polynomial. I want to make sure this density is the slope relationship holds up for weirder wavy shapes.
Okay, let's use a trigonometric wave. We have a source example defining a density where f of x equals 1/2 sine x restricted to the interval from 0 to pi.
All right, let's test the relationship in the derivative direction first.
So if you calculate the running total, the CDF is 1/2 times the quantity 1 minus cosine x. If we take the derivative of that CDF, and remembering the derivative of cosine is negative sine, the double negatives cancel out nicely, you are left with 1/2 sine x. So f of z equals f prime of z perfectly. The density is the exact slope of the CDF, even for a trig wave.
Nice. Now let's do the area check. If this is a real density, all the probability under that sine wave curve has to add up to 1, right?
Yeah. We check if the total area under f is 1. We take the integral of 1/2 sine x from 0 to pi. The antiderivative of sine is negative cosine, so you evaluate negative 1/2 cosine x top minus bottom.
Okay, let me think. Plugging in pi gives -1, and plugging in 0 gives +1, so the negatives cancel out.
Right, it gives you 1/2 times the quantity 1 plus 1,
Right.
which beautifully simplifies down to exactly 1.
The total area is 1, so it's a completely legitimate density.
Exactly.
And if I wanted to find the chance that my variable lands in the first half of that wave, like between 0 and pi over 2,
You just find the area up to that halfway mark. The area under f from a to b, evaluated from 0 to pi over 2, comes out to exactly 1/2. Probability is area.
it is deeply satisfying to see that work so cleanly on a pure math curve.
Yeah.
But let's apply this toolkit to a messy physical measurement. What is next in the source material?
We have an example analyzing measurement error in a chemical reaction temperature.
Okay, real-world stuff.
Yeah. The error, which we call x, has a given density, and f of x equals x squared over 3. This is specifically for x between -1 and 2. The density is 0 everywhere outside that range.
So we have a small parabolic curve representing our measurement error. First things first, we have to verify this is a legitimate density before we use it.
Right. Check 1. Is it non-negative? Yes. Any real number squared is positive or 0. So x squared divided by 3 is never negative.
Makes sense. And check 2 is the area. All the shaded space under that little piece of parabola has to equal exactly 1.
So we need to integrate x squared over 3 from our bottom limit of -1 up to our top limit of 2. Using the power rule, the antiderivative becomes x cubed over 9.
Okay, now we evaluate top minus bottom. The top boundary is 2. 2 cubed is 8, so that gives us 8/9.
Right.
The bottom boundary is -1. Wait, -1 cubed stays negative. So the bottom evaluates to -1/9. I am subtracting a negative.
Exactly. You have 8/9 minus -1/9. The double negative makes it addition. 8/9 plus 1/9 equals 9/9, which is exactly 1. Both our required conditions hold perfectly. That specific slice of parabola is a valid density.
Awesome. Since it is valid, let's use it to answer a practical question about this chemical reaction. What is the chance that the temperature error lands between 0 and 1?
We just want the area of that specific center slice. We integrate x squared over 3 from 0 to 1. We already have the antiderivative, which is x cubed over 9. We plug in the top limit of 1, which gives 1/9. We plug in the bottom limit of 0, which is 0.
And 1/9 minus 0 is just 1/9. So there is roughly an 11% chance the measurement error falls in that exact window.
Yes. And you can build the entire continuous CDF with a complete S-curve for this temperature measurement simply by accumulating that area up to any generic variable x.
Oh, I see.
For values inside our window, the CDF, fx, evaluates to the quantity x cubed plus 1, all divided by 9.
Let me test the limits of that S-curve formula just to prove to myself it behaves the way a running total should.
Go for it.
If I plug in the absolute bottom of our range, -1, well, -1 cubed is -1. Plus 1 is 0. 0 divided by 9 is 0. It starts with 0 probability, exactly as it should.
Perfect. And if you check the absolute top of the range?
The top limit is 2. 2 cubed is 8. Plus 1 is 9. 9 divided by 9 is 1. The running total hits exactly 100% by the end of the interval.
Yep. And if you take the derivative of that CDF formula, the power rule drops the 3 down, the 1 disappears, and you get right back to x squared over 3. The density and the CDF are entirely locked together.
Okay, but what if we reverse the process? Our sources verified a density first, but can we start with a really intimidating running total, like an ugly CDF, and use it to find the density?
There is a fantastic example of exactly that. Imagine a CDF where f of x is 1 over pi times the quantity arctan x plus pi over 2.
Oof, that sounds messy.
It looks incredibly complicated, but we just walk through our standard checks.
All right. A valid CDF has to stay bounded between 0 and 1. Does this formula actually do that?
It does because of the nature of the arctan function itself. The arctan graph is strictly trapped between negative pi over 2 and pi over 2.
Oh, right.
When you substitute those extremes into our formula, the negative pi over 2 cancels out to 0, and the positive pi over 2 adds up to pi, which divides by pi to become 1. The entire expression lands perfectly between 0 and 1.
Okay, wow. The second check is that it has to be continually increasing. A running total of probability can never dip back down.
But we verify that by checking the slope, the derivative. The derivative of arctan is well known. The derivative of the CDF is 1 over pi times the quantity 1 plus x squared.
Okay.
It's because x squared is always positive, that denominator is always positive, the slope is always positive, the curve never decreases.
And the third check, which we just essentially did, is that the far left limit infinitely approaches 0, and the far right limit infinitely approaches 1. It passes all the checks. It is a valid CDF.
And that derivative we just found to check the slope, that is our density.
Wait, but this creates a geometrical paradox in my head. That density formula 1 over pi times 1 plus x squared, it creates a bell-like curve, but it is spread out over all real numbers.
Yeah, it is.
It stretches infinitely to the left and infinitely to the right. It never actually touches the 0 axis. How can an infinitely wide shape contain a finite total area of exactly 1?
It feels completely counterintuitive until you visualize the asymptotic squeeze.
The what?
The asymptotic squeeze. The tail of that curve gets thinner much faster than it gets longer. As it stretches out toward infinity, it is squeezing down against the axis so rapidly that the area you are accumulating essentially vanishes.
Oh, I picture that.
Yeah, an infinite horizontal spread can perfectly bound a finite measurable area of 1 because the height is collapsing towards 0 fast enough to cap the total volume.
That actually brings us to a final, very related exercise from the sources. We have a specific kind of infinite density that pops up everywhere in the real world.
Right, we are looking at a thin-tailed distribution, specifically a density that decays like a power. The formula is f of x equals 3 over x to the 4th for any x greater than 1.
So it starts at 1 and stretches out to infinity. The area checks out as valid. And the CDF for this, f of x, evaluates to 1 minus 1 over x cubed.
So using that CDF, what is the probability that your variable x exceeds 9?
Well, we want the probability out in that thin tail, past 9. So we calculate 1 minus f evaluated at 9. The ones cancel, and we are left with just 1 over 9 cubed. 9 cubes is a big number.
9 cubed is 729.
Right. So the exact area out in that tail is 1 over 729.
Which is approximately 0.0014. It is an incredibly tiny sliver of probability.
To connect this mathematical shape to reality for you, this thin tail perfectly models physical phenomena that are almost always small, but occasionally turn out to be massive. The tail gets vanishingly thin, but it never completely closes off.
Yeah, and once you recognize this power law shape, you see it everywhere. Earthquake magnitudes, massive financial market crashes, extreme weights for network servers.
Right.
The vast majority of the time, the values cluster harmlessly on the left. But because that tail stretches to infinity without ever hitting 0, those truly massive catastrophic events are always mathematically possible. They are rare, residing in that 0.0014 area, but they are not impossible.
Let's pull the mechanics of this paradigm shift together. When we are dealing with outcomes that fill an interval, we abandon counting discrete steps. We adopt the continuous CDF, which visually is a smooth, flowing curve.
And the steepness, the slope of that smooth CDF curve is your density.
Probability physically transforms into geometric area. To verify that a density is mathematically legal, you ensure it never dips into negative numbers, and you ensure the total area under F is 1. And perhaps the strangest takeaway. Because of this smooth continuum, the probability of any single exact value is 0.
That perfectly encompasses the shift from discrete points to continuous intervals. Everything we have discussed today has been about answering one fundamental question. Where does a variable land in a given range?
But the sources hint at a different way to look at this, don't they?
Yes, they do. Next time, the mathematical framework shifts once again. Instead of asking where a variable lands in a single instance, we are going to look at expected value.
Expected value, okay.
We will ask, what does this variable average to over the long run? We calculate that by taking every possible outcome and weighting it by its probability, or its density, to find the true center of gravity for the long-run average.
So we are moving from asking where does it land this time
Yeah.
to asking what is the typical value over time? Which brings me right back to my frustrating coffee mug this morning.
Exactly.
The exact probability of me hitting that microscopic fill line on any given morning is 0. I will always be a tiny fraction off. But over the course of an entire year of mornings, tracking all those tiny microscopic misses over and under the line, what is the average level of coffee in my mug? That is exactly what we will figure out in our next deep dive into the source material. Keep that shift in mind, from tracking individual shaded areas to finding the long-run average as you mull over today's discussion.